Our next speaker is Dr. John Yeow. Dr. Yeow is going to present to us this afternoon, continuing on the theme of nanomedical structures and devices in development today on the topic of flexible and transparent dosimeters for radiation oncology applications. So I think, very consistent with a theme that we have heard during the course of today of radiation oncology and nanostructures being two things that work hopefully very well together. Dr. Yeow is coming from not too far away at the University of Waterloo. Please join me in giving a warm welcome to Dr. Yeow.
Thank you, Dr. Rothblatt, and thanks to the organizer for inviting me. Okay, so I belong to University of Waterloo, and I'm also representing Art Sensing Incorporated, which is a spin-off company from my lab, currently located at Waterloo Research Technology Park. I'm going to talk about, the talk so far has been using nanostructures, nanoparticles, or carbon nanotubes within the body. I'm an engineer, so we actually built devices using nanomaterials that would work outside the body. So just an outline of what to expect within the next 20 minutes. I'm doing an introduction of why we are doing what we are doing, what is the role of dosimeter for radiation oncology applications. There's several different technology we're currently developing. One of the key technology is quantum dot-based radiation dosimeter or radiation detector. I'll present our experimental setup, experimental result, which is quite promising, and also I'll talk about devices that are currently available through Art Sensing, but the technology would be based on a different sensing material than I'm going to present here, but nonetheless, what I'm going to talk about here would give you an idea of the potential. So radiation description, basically we use every single morning in Cancer Center where we use linear accelerator or X-ray to generate X-rays or E-beam to treat cancerous tissues. We have to characterize the X-ray machine just to make sure that the oncologist prescribe a certain dose to a certain location on the patient's body. We are delivering the correct dosage, as well as delivering it to the correct location. And our application is not just for treatment X-ray, but also for diagnostic X-ray. For a patient to go to a hospital to take an X-ray picture taken, it is now your right to know how much dosage has been delivered to your body. So our application traditionally has been measuring the amount of X-ray delivered during cancer treatment, but nowadays there's a lot of work into measuring a diagnostic X-ray as well, such as CT. Every single morning in the cancer center, they would have different sorts of technology to calibrate the X-ray machine. And as well, besides characterization of X-rays from the LINAC machine, dosimeters are also placed on patient's body to measure the actual dosage to skin surface. There's different type of conventional technology. One thing you have seen radiation therapists wearing different badges. Those are based on TLD technology, thermoluminescence dosimeters. They're durable, that's why they're used widely, but they do not give you instantaneous reading of radiation dosage, which means that if you are overdosed, you would not know until 3 months later. So that's the major disadvantage of using TLD, but again, it is an extremely cheap technology. Other ways of characterizing a LINAC machine involving a traditional X-ray film. So we would place an X-ray film underneath a LINAC machine, and profile could be generated from the image generated on the film dosimetry. The advantage is it's not really real time, and it can only be used once. Other newer technology involve integrated circuit technology such as the MOSFET dosimeter, which is a lot smaller. It gives real-time instantaneous reading, but the disadvantage is it's extremely expensive and the readout is extremely non-linear. It's dependent on humidity as well as temperature. So what works today might not give you the same reading tomorrow. The gold standard for characterizing an X-ray machine is the ion chamber. Now the ion chamber never breaks down, it gives real-time reading, but the size of ion chamber is extremely big. And so the bigger the ion chamber you build, the higher the signal-to-noise ratio. Again, for the newer type of cancer therapy, radiation cancer therapy applications, we want a high resolution or spatial resolution reading of cancer or X-ray beam in a 3D, 2D format. So right now, I'm working with Princess Margaret Hospital in Toronto, and this is a conventional ion chamber dosimeter that is used to profile a LINAC machine. This is a machine that is used to irradiate cancer tissues in the cancer center. So every single morning, we would have to characterize this machine just to make sure that it is, in fact, giving the correct doses to the correct places. As you can see, it's extremely big. I'm not too sure if you can see clearly here. There are dots on this 30 centimeter by 30 centimeter panel. There's a total of 49 sensors on there. Extremely sensitive, but does not give the required spatial resolution on that 2D plane. Well, there are technology out there that would provide high spatial resolution imaging, and this is one of our competitor, Sun Nuclear, which has probably 60% of the market today. They are using diode technology, again, integrated circuit technology that would break down over time. So the lifetime of this thing is probably about 2 years, and every 2 years one would have to change a panel like this, and this would cost about $50,000. Other competing technology is, this is a MOSFET technology, extremely small, but it has a finite lifetime. So it probably worked for 3 months, then one would have to replace that technology. Well, the problem is we do not have the required spatial resolution, especially for IMRT. I'll talk about IMRT application in the next slide. And they also do not provide long-lasting, minimally invasive, real-time monitoring of delivered dose. So, can I just run this video, please? So the first video you're going to see is a patient with a tumor within the body. The patient sitting on or sleeping on a couch. You have the LINAC machine that generates high energy X-ray beam to target a tumor within the body. And obviously, very often, there's healthy tissue in the way, and we would damage the healthy tissue as well as the cancerous tissue that we try to attack. So the next video at the bottom, we have different technique to mitigate that problems. Here, the LINAC machine really just generate a flood of X-rays. So it generates a flood of X-rays, and we have collimators on the LINAC machine that actually move across. So it's really intensity modulated radiation therapy, which means that we modulate the intensity delivered by modulating the time of exposure to tissues. So you have a collection of really tiny lead fingers that go from one side to the other side. So the slower it moves, the more exposure you have to radiation beam, the faster it moves, the less radiation one would get. So if I could run the video on the left-hand side, here a typical movement of the lead fingers from the left side to the right side. And on the left side, this is an image that is developed on a film. as you can see, by controlling the speed of the collimators, we can sculpt out different images, as demonstrated here. The white portion obviously has more photons. The black portion has less photon delivered to it. So by time modulating X-ray delivered, we can actually change the amount of photons tissue received. So in the resolution we're looking at, it's about 2 millimeters. So you're looking at 2 millimeter in width for the lag fingers. So today, the dosimeter requirement of these, it's actually looks like trivial requirements, but they're extremely difficult to build. We need a highly sensitive radiation sensors. Nowadays, we are giving less dosage over a longer duration of time. So we need a sensor with higher signal-to-noise ratio because of new technique like IMRT. We want high spatial resolution imaging in 2D. We would also require low power consumption as well. Also, not only the capability of point source detection of radiation beam, but rather a 2D profile of radiation beam. The future requirement also require minimum radiation attenuation through the sensing device. So the technology that I presented is a offline calibration of the LINAC machine. And our sensor, what we're trying to do is, instead of doing calibration on the machine every morning, we want to develop a sensor that could be placed on the patient's body, so we could treat the patient and at the same time measure the radiation delivered in real time during treatment. So here is an example of a QD-based radiation dosimeter that we have fabricated in the clean room. You're looking at a device here. This is one die with about 12 elements on it. So on a 2D area, we have 12 sensors on there that would detect the profile of X-ray in 2D. So why quantum dots is used? Well, quantum dots, as we all know, is a quasi-zero dimensional material. So it has an extremely good electron transport property, which means that in a traditional bulk semiconductor materials, obviously we have the conduction band and the valence band. So when we expose these semiconducting materials to photons, photon would excite electrons from the valence band to the conduction band. So in bulk semiconductor materials, a lot of the photons which does not have the energy to overcome the barrier between the valence band and the conduction band is wasted and manifests itself by heat through complex electron-photon scattering phenomenon. But quantum dots, because of its quasi-zero dimensional structures, it has within or between the valence band and the conduction band, it has many intermediate bands that electron could jump onto, so one would have secondary effect of other photon exciting it in stages from the valence band to the conduction band, and hence increasing the amount of electrons that can change the conductivity of the semiconductor over time. So because ionization radiation is one of the major problem for current technology like MOSFET or diode, because they're made of integrated circuit silicon, so it degrades over time. So I think I'm running out of time here, so I'm going to slip a lot of slides. Here is an experimental setup that we have to characterize our device. You can see here is a LINAC machine that is used to characterize a dosimeter. And here a really beautiful response, in quite linear response to energy, photon energy. As you can see, it responds to many different mean photon energy that would just says that quantum dot is a potential material that could be used for radiation detection. So we have used two types of quantum dot. One is cadmium telluride, the other is zinc oxide. Cadmium telluride has a better response just because the band gap between the valence and conduction band is much smaller, and hence we have a lot more electron that could be excited and contribute to the bulk current. And here is a characterization experiment where we increase the electrodes between the quantum dots. As expected, the signal-to-noise ratio degrades because we have less quantum dot that could contribute to the overall current generation. Here is obviously as we increase the amount of quantum dots within our sensing material, we have a huge increase in performance as well. Some experiments were to demonstrate the repeatability of our sensors. Here is the base current with the radiation off, and here is the response current when the radiation is on. As you can see, the response is very, very repeatable. And the potential of this is, besides the capability of high-resolution imaging or high-resolution calibration of LIDAC machine, one could build a transparent dosimeter, and this is optical transparent, but more importantly, it is transparent to X-ray as well. And I have mentioned that if we could spin this material on a glass surface, it would be a transparent dosimeter. If we spin this material on a flexible surface, it would be a flexible dosimeter that could conform to any body structure. And so now we could deliver X-ray to specific location of the body, and at the same time treat and measure, which no other sensing or dosimetry sensing technology could provide today. So Art Sensing, just a little bit of information of the company. Art Sensing is located in the Accelerator Center at Waterloo Research Technology Park. We have already on the market flexible dosimeter that conform to any body structure, and that will give you the surface dosage of X-rays or E-beam that has been delivered to cancerous tissues. We also have high density sensors on the order of 2 millimeter by 2 millimeter in squared, and we have a single substrate that could have 1,600 sensors on a 10 by 10 centimeter squared area. So we could provide extremely high resolution, spatial resolution imaging of X-ray beam. And at the same time, we could actually profile and treat patient at the same time. Here are some exciting specs of our dosimeter. As you can see, it's extremely repeatable with the X-ray off and X-ray on. Here is a 3 millimeter by 3 millimeter flex DOS, which is a flexible dosimeter. Again, it has beautiful repeatability results, and it is extremely sensitive. I believe this is an X-ray of 120 kilo electron volt X-rays that was used as for this characterization experiment. Again, our sensor works down to less than 2 volts, so it has operation of less than 2 volts. And as we decrease the operating voltage, the signal-to-noise ratio increase, and obviously that's predictable just because the base current that we work with, it's a lot smaller. And the other thing I want to touch upon really quickly is my other projects that would come into the final device that we want to build. One thing about carbon nanotube, besides the fact that it has amazing thermal property, is that once you put carbon nanotube within 2 capacitors, each one of those carbon nanotube would act as electron guns. So if we have access to electrons, we could generate X-rays. So in my lab, we are making a miniaturized X-ray machine that's shown here. This is a desktop system. The final goal is something on the size of 2 centimeter by 1 centimeter. We are also building ultrasonic transducer on the order of 1 millimeter by 1 millimeter. We're also making micromirrors that could direct laser beam for optical detection applications. If you can run the video, please. And in 2003, we have actually acquired with optical coherence tomography the central nervous system of a fruit fly. You can see this is the central nervous system with nerve ending going on both sides. This is a 3D picture of this cartoon here. So my point is, really, we have the technology, optical imaging technology. We also have the ultrasonic imaging technology on a really small scale. So where do we want to go with this? We want to build the ultimate device. Now, within an endoscope, obviously, endoscope would deliver X-ray beams to the very distal end, and we insert this into human cavity for in vivo biomedical imaging. With the micromirror that I have demonstrated, we can see that we can actually image structures in the microdomain. So coupling it with ultrasound modality, we could provide multi-modality imaging for optical biopsy, detection of cancers, and at the same time, if we can miniaturize an X-ray machine and integrate it at the tip, distal tip of an endoscope, we could shoot photons in the right locations. But obviously, at the same time, if we want to treat patient, we want to make sure that we're delivering the correct dosage. And with Art Sensing's flexible dosimeter technology that is transparent to X-rays, we could deliver X-rays and treat cancer cells and detect the amount of dosage delivered at the same time. So of quick conclusions, we have demonstrated that nanotechnology could be used that will provide real-time measurement of X-ray delivery during treatments. And right now, our technology would be delivered to a cancer center near you. Obviously, this work is not just that of my own. I have to thank my graduate student who has been involved in the project for the past 5 years, and my collaborators in the hospital as well. Thank you.
Thank you very much, Dr. Yeow. This is, I would have to say, the most exciting application I've seen in radiation therapy in terms of miniaturization of the technology. So I really applaud you and your team on your work.
Thank you.
I'm sure there's some questions for you, and after that we will take a 20-minute coffee break. Please introduce yourself and your affiliation.
Melanie Swan, MS Futures Group. I was wondering if you know how the art scanning would compare with radiosurgery, such as from Accuray, that does the tri-directional pointing for myeloma and prostate cancer treatment.
Are you referring specifically to our X-ray delivery technology? Well, like I said, our technology would have advantage where you could have direct access to it. So the X-ray probe would have to be inserted to that location in order to deliver photons to that locations. So in terms of comparison, I would say that it really depends on the application or the type of cancers that you want to treat. For our technology, because you can imagine that we have better resolution and better control, because you are delivering photons on spot. So one could have really huge control over the endoscope. So the dexterity is there, so it can move in 6 degrees of freedom in real time. So again, it really depends on what kind of application you're looking at. But the Accuray technology is also a beautiful technology. But again, the photon is generated from outside the body.